We're going to talk a little bit about taking measurements and taking measurements appropriately. So the reliability of your measurement is going to depend on the kind of instrument you take it with. You need to, anytime you're taking measurements, try to find the most reliable piece of equipment that you can. And so the example here talks about a bathroom scale versus a butcher's scale. So the bathroom scale can differentiate between, say, 65 and 75 pounds. But if you put something on there that's 1.65, it can't tell the difference in that and 1.75 because the bathroom scale doesn't have that much precision. A butcher scale, however, is going to go to 2 decimal places, and so you would be able to differentiate between smaller differences. So scientific measurements are recorded so that every digit is certain except the last one, which is estimated. Now, if you're using a digital scale, all of the digits are certain. Okay, you record everything the digital scale shows you. But if you're using an analog scale, like these two examples in the pictures here, then you're going to estimate 1 decimal place past the markings. Okay? So if it's marked to the ones, you estimate to the tenths. If it's marked to the tenths, you estimate to the hundredths. If you have something that's only marked to the tens place, the best you can do is the ones. So you can't, if you have a piece of equipment that is marked every 25 milliliters, then you can't put that it's 24.72 milliliters because you wouldn't know that kind of reliability in your measurement. So we're going to take a look here at what we can assume is a graduated cylinder over here. Okay, graduated cylinders used to measure volumes of liquid. And so this curved surface at the top of the liquid, that's called the meniscus. And so you're going to always measure from the bottom of that meniscus. Sorry about that. So you have the curved surface, that's the meniscus. You always want to measure from the bottom of it. So in this case, we look at our scale. It's got a tick mark for every 1 milliliter. So if it goes to the ones, we're going to estimate to the tenths. And to me, it looks like this one. Okay, so we know we're between 20 and 30. And we know we're between 20 and 25. So it to me looks like it is just underneath that fourth tick mark. So I would probably record this as 23.9. You might say 24.0 as you think it's right on it. As long as you're in the ballpark around that measurement, around 24 milliliters, the estimated decimal place doesn't matter. It's just that you have the right number of decimal places and that it's in the right area. So this other picture is a triple beam balance, which we don't use very often. We have digital scales for measuring mass. But the way you read these, they have 3 sliding scales. The back is the tens, the middle is the hundreds, and the front is the ones. So you start at the hundreds, go to the tens, and then to the ones, and you add it all together. So we're at 260. Okay, so we know that. Then in the ones, we're between the 5 and the 6, so 265. Since this is the major marks are 1, that means the little marks are going to be the tenths. So if it's marked to the tenths place, we're going to need to estimate to the hundredths. So this is going to need 2 decimal places. And so we look, that's between the 7th and 8th marks. And to me, it looks like it's a little closer to the 7 than the 8. So 265.73. Again, you might have said, well, it looks like it's exactly halfway between, so you put 265.75. This is the part that's certain, 265.7. That's the part that's estimated, that last decimal place. Okay? So it doesn't have to be exact what someone else reads. All right, let's take a look at some data. So here we have, and I'm going to make this a little bigger. There we go. Here we have some data collected by 3 students, and they were measuring the mass of an object. Okay, and that object's true mass was 10 grams. So this is our actual measurement. Okay, That's what it should be. And so the students measured it 4 times each and recorded their masses. And so we look at student A, they're kind of all over the place. And so we say that they have very low precision. The precision of measurements is how close a set of repeated trials are to each other. So their measurements are kind of here and there. There's some above the number, some below the number. Their average comes out to be 10.13, which is a little bit off from that actual. So that's their accuracy. Their accuracy is not great either. Okay. And we can look at student A's data here. If we draw a line where the data is supposed to be, it's supposed to be 10 grams. You can see that those bar graphs just don't really match. So student A is neither accurate nor precise. So then we go to student B. Student B's measurements are all within 0.07 of each other. They're very, very close. So student B's precision is really, really good. And again, we draw the line in the graph here at the actual measurement. You can see that all of their data is consistently below, okay? And they're very close to each other. So student B is precise. Their measurements are close together, but not accurate. And then finally we get to student C. Student C has 0.05 difference in their measurements. Their average is at 10.01, so when we look at it graphically, there's that 10 line. And if I had drawn my line straight, they would have all been flat on the line. So student C would be both accurate and precise. Student C is the exemplary student here in their measurements. Okay. So let's talk about the errors that student A and B had. A random error is one that has equal probability of being too high or too low. So student A is showing random errors. They have some measurements that are too high, some that are too low, but all measurements have some degree of random error, okay? So anytime you take a measurement, there's going to be a little bit of error. Tends to average out over repeated trials. Now, student A got kind of close, but not really, really good either. But it's closer than student B, who has a systematic error. Systematic error means they're measuring it the wrong way, the same way every time. So a systematic error tends to be due to something with the equipment that's being used. It's uncalibrated or it's just not reading right. Okay. But their average is worse, further from the real number, because they're consistently too low. And so in the next video, we're going to talk about significant figures. Significant figures are used in data representation to indicate the certainty of a measurement. Some equipment is going to allow for more certainty than others, and that's one of the reasons that it's important to learn about lab glassware and what it's used for and what it's, what's better for some things than other. Okay. So we'll pick up in the next video with significant figures.